Hello, we are the Aerojet Rocketdyne remote-controlled rover payload team. This is our final presentation for senior design. Our team is Chris, Joelle, Angeli, and Chase. So the motivation for this project is that the sponsor, Aerojet Rocketdyne, wanted to fund some students to make a project for entry to the FAR Rocket competition. This is a competition in California that consists of creating a rocket and a payload to complete a competition goal. There are multiple goals to choose from, but we chose the reconnaissance vehicle payload. We chose this because we're interested in implementing the wireless communication and control implementation that comes along with creating a remote-controlled rover that transmits live video. So we have four main goals and objectives driving this project. The first is to create a payload that mates with a rocket and can deliver a rover to the ground. Second is to create this rover to have remote-controlled abilities and to transmit live video back to the control station. Third, our rover and capsule would have to have a mating system for secure landing. And finally, all of our systems should have battery power for unhindered mobility. Our three main requirements driving our system are our rover will respond to controller input within 10 seconds. It'll be able to turn 360 degrees in 5 seconds, as well as move forward and backwards. And finally, it has to travel 3.05 meters or 10 feet from the landing site in 15 seconds, as required in the FAR competition rules. So now we'll go into our design overview. We'll talk about our rover, capsule, and RCS or rover control station separately, and then we'll talk about the total system together.
The Rover. The Rover chassis will be a light steel frame that mounts the PCB, video camera, motors, and the power supply. Rubber tires with aggressive treading will be used for the movement system to allow the rover to avoid terrain hazards. A LiPo battery cell will be used to power the PCB, camera, and receiver. A rechargeable 11.1-volt battery will power the motors and transmitter. The PCB will control all the remote control reception and translation operations, as well as the video transmission and rover auto start system. Here's the fully assembled and manufactured rover with wheels and all electronics on board, which are secured using standoffs and Velcro. The capsule. The capsule and rover are to be mated using an electromagnetic coupler. The PCB will be responsible for sensing when the capsule has landed and for releasing the coupler to allow the rover to begin its mission. It will have its own battery and will be electronically disconnected from the rover. Here's the manufactured capsule. The photos on the outside and bottom are the capsule post-flight, and the one in the middle is the recently manufactured capsule before it had been outfitted with any of the payload integration parts and assemblies. The rover control station. This controller and video receiver unit will be freestanding from the rover. It will have its own rechargeable power source to allow it to be moved freely. It will receive and display the wireless video signal from the rover in 480p. It will have a joystick used to control the movement of the rover via radio transmission as well. This layout on the right shows where each of the components will be on the RCS board. Underneath the board is where the battery packs are going to be attached by Velcro. Here's the fully assembled and manufactured rover control station with the components laid out as was previously outlined on the last slide. Looking at the system overall, the capsule will be loaded into the rocket airframe with the rover inside of it. The capsule system will then be powered on and be waiting to detect liftoff. The rocket will lift off and the rocket will reach 10,000 feet before it starts descending. The capsule will be ejected from the rocket and descend via parachute at 1,000 feet. When the capsule lands, it will detect the landing, and the rover will be released from its electromagnetic coupler, and it will be able to drive out freely. At the control station, it will be seen in the video reception that the rover has landed with the capsule, and the rover will be piloted for a minimum of 10 feet to complete the mission. Membership responsibilities. I, myself, Chris, was in charge of the rover and capsule design as well as the manufacturing. Joelle was responsible for the video transmission system and PCB design. Angeli was in charge of the remote control system and as well as PCB design for that system. And finally, Chase was overseeing the power system, the sensing systems, and the PCB design for those. Looking at the overall block diagram, the rover is going to be inside of the capsule, and that subsystem will communicate with the control station. In the capsule block diagram, the capsule PCB takes in data from the altimeter and accelerometer and processes this data to detect the landing conditions, and it will then in turn tell the electromagnetic clock to unlock. In the rover block diagram, motor control instructions are received via the radio receiver and are then translated to the rover PCB. At the same time, the camera is sending a signal to the rover control station via the video transmitter. In the rover control station block diagram, the RCS PCB takes an input from the joystick, and this input is then relayed to the rover via the radio transmitter. At the same time, video data is received from the rover via the video receiver and is then displayed on our 480p display. Rover chassis design. Our rover was designed to be fit within a diameter of approximately 14.5 centimeters in order to fit within the capsule and in turn the rocket payload bay. Our rover was designed to fit the largest electrical components in its bed, and a small cutout was made on the front of the rover to house the video camera, as well as other cutouts for wire pass-throughs. Our rover was manufactured using AISI 1060 steel sheet. These steel sheet pieces were cut and riveted together using a jigsaw and rivet gun. Anchoring points were added for the electrical components, and custom wheels were fashioned from gears. The motors were attached to the bottom of the chassis using custom aluminum housing. Capsule structural design. Our capsule was designed with key geometric features that allow for successful upright landings. The scoop feature on the front of the capsule guides the capsule to land on its landing gear after initial contact with the ground. The planned force balance within the payload will induce an angle of attack with the purpose of landing the capsule in the proper orientation. Our capsule was manufactured using AISI 1060 steel sheet. This sheet was cut into pieces and welded and riveted together using a jigsaw, welder, and rivet tool. 2 eyelet screws were attached to the back of the capsule for parachute anchoring. The railing and sled were custom manufactured out of aluminum and plastic.
The 2 voltages we need in this project are 3.3 volts and 12 volts. Any voltage regulation circuits we used were designed using the TI Webench software. We created a 3.3 volt buck boost circuit and a 12 volt boost circuit. Both of these have inputs from our 3.7 volt LiPo batteries, which we will show later. So for power supplies, we use a mix of 11.1 volt and 3.7 volt LiPo batteries. The 11.1 volt batteries are used for our rover, its motors and video transmitter, and the RCS, which needs the video receiver and video screen powered. And our 3.7 volt batteries are used for the ICs and MCUs on most of our boards, as well as the boost circuit on the capsule board to power the lock. So here are some power supplies. We'll go through the next couple slides and show how we made our choices. So the rover power supply uses a 3000 milliamp battery. Its second power supply is 11.1 volt RC battery, which can handle the high current draw of the motors. The capsule uses a small 3.7 volt battery. The RCS uses a really large battery that we already had purchased, so we just use this so we don't have to buy another battery to spend more money. It also uses another 11.1 volt battery, which we had to buy last minute, so we didn't want the unconventional type of battery, but it provides the voltages we need. Next, we'll talk about our landing sensing system. This system will allow the user to Next, we'll talk about the landing sensing system. This system will allow the capsule to automatically unlock the rover from its coupler when it lands. This is necessary because the user may not have line of sight on the capsule during landing, so an automatic system must be used. This is done by an MCU checking a sensor for landing until the correct orientation is found. Here's the block diagram of this system. So when the system starts, we will first check for liftoff via 4Gs of acceleration. After this happens, we will consistently check to see if the payload orientation is flat or the z-axis experiences roughly gravity. Once this happens, we'll start a 5-second timer, and if the payload orientation is flat for this entire duration, then we can guarantee we've landed. We know that at apogee the rocket will level out, but after talks with the rocket team, we determined 5 seconds was enough time. So to detect this, we use an accelerometer. We chose this first accelerometer mostly because of its breakout board availability and ease of programming. All 3 boards we created use the MSP430 MCU. We chose this MCU because with the embedded systems class, all 3 ECE team members are very familiar with this chip. We also all have launch pads, which allows us to easily program this chip and use the debugging and UART functions of the launch pad to help us with our programming.
Rover and capsule coupling. To prevent the rover from moving inside the capsule during flight, a coupling mechanism was needed. We selected an electromagnetic clock due to its form factor and high strength. When landing is detected by the capsule, the load switch connected between the power source and the coupler will be open to allow the rover to drive away.
To control the coupler that we're using, we have to use a load switch. Since our coupler is toggled by power being on or off, we use a MCU controlled load switch to unlock our coupler when the capsule has landed.
Rover propulsion mechanics. We chose to do differential steering for our steering mechanism, which requires 4 motors. Each motor must have a minimum of 0.45 kg-centimeters of torque. Each motor must have a minimum of 97 RPM to meet the requirement of 10 feet in 20 seconds, assuming a 4 centimeter wheel diameter.
To control the speed and direction of our motors, we'll be using PWM and GPIO from our MCU on the board. Each pair of motors will share direction and speed signals, and the motors are powered by the 12-volt power rail of the Rover board.
For the Rover remote control, we were debating between using tactile buttons or an analog joystick. We decided to go with the analog joystick because we felt it would be easier to use. The analog joystick works by providing coordinate points of the joystick's position. These values range from 0 to 4080, where the resting point is theoretically 2040-2040. The coordinate values are classified into forward, backward, left turn, and right turn based on the diagram shown. For the radio transmission, our two choices were the RayX long-range transceivers that used SX1276 or SX1278. We had to choose the RayX RYLR896 module because we had to avoid the 433 MHz frequency to avoid interference with the rocket. The radio transmission is used to transmit the data from the joystick. It can be configured to use 868 or 915 MHz range and uses AT commands. We want the transmission to work over a distance of 2 kilometers so the receiver on the rover can relay the information to the motors. This diagram shows how the transmitter side from the rover control station will work. The data from the joystick goes through an analog digital converter where the X and Y axis values are stored into the two registers. Based on these values, some logic operations will determine what directional control to send. This message is written into the UART transmit buffer, one character at a time, to then transmit to the receiver. The receiver on the rover receives the message character by character into the receive buffer and is stored into an array to reconstruct the message. The array is set so that the directional control letter is always stored in position 11 of the array. So by reading this position, we can determine how the motor should move.
For our wireless video capture, video will be captured on the rover using an FPV camera, which will capture at a resolution of 700 TVL. This video will be fed out into the transmitter in NTSC format. For wireless video transmission and reception, the transmitter will send out the video signal along one of the different 5.8 GHz bands it can select from, and on the receiving end, the receiver will receive that signal and output it to the display via an AV wire. For our display, we have an 800 by 480 pixel monitor, which will get the feed from the receiver, and the monitor will be attached to the rover control station to provide a live video feed to the rover operator. Here are wireless video transmission choices. The one on the left was chosen for its known compatibility in between the transmitter and receiver and availability. For our video camera choices, we chose the one on the right, known for its out-of-the-box compatibility with most FPV transmitters. And for our video screen choices, we chose the 5-inch screen on the left for its lower price and smaller size.
Here's the schematic for our Rover PCB. You can see both regulators that we're using, and this board is special because it's the only board with an 11.1 volt input from the RC battery we discussed earlier. We also can see the accelerometer and altimeter on our board, as well as the radio receiver and video transmitter headers and the motor headers. Here's the layout of our board. It measures 7.2 centimeters by 10 centimeters.
Here's the capsule PCB schematic. And here's the capsule PCB layout of that schematic.
Here's the rover control station schematic, which has the headers for the video receiver, screen display, the joystick, and the radio transmitter. It also has the analog digital converter and 3.3 and 12-volt regulators. Here's the PCB layout for the Rover control station, which is 7 by 6.35 centimeters.
Our primary engineering constraints were that the payload capsule and payload must be able to withstand up to 8 Gs when the drogue chute deploys, as well as during the launch acceleration. The payload must also be unaffected by operation in the radio frequency ranges of 420 MHz to 450 MHz, as well as 1 GHz to 2 GHz. Finally, the payload dimensions must be less than 14.5 centimeters in diameter and 40.64 centimeters in length. Environmental and sustainability constraints. Our project was designed in a way that it will not create litter, and all parts used will be harvested and reused after the mission. Rechargeable batteries were chosen to reduce the waste, and one-time use technologies were avoided. Consideration was made for the way the sandy terrain of the target operation environment could impact the rover as well. Manufacturing constraints. Due to potentially harmful side effects of the manufacturing techniques used in this project, such as soldering, torch welding, and plasma cutting, special care and safety measures will be taken to prevent bodily harm. The silicone shortage placed extreme pressure on both the team's ability to source parts as well as the budget. The increase in prices of the shortage, along with inflation, caused the team to go over budget, with prices of multiple components increasing by 200% since fall 2021. Ethical constraints. The team explored ethical considerations when creating the design of the system to make sure no harm is done to the public. The conclusion the team reached was to keep the operation of the rover restricted to group members, so the electronics aren't used without regard for typical ethical considerations. It was concluded that there will be hardly any impact on humans because this project will not be used commercially and will be used in a regulated environment. The team still maintained the ethical considerations regarding the environment mentioned in a previous slide.
For our project, adhering to safety constraints was very important due to the volatile nature of rockets. Some of the constraints we adhered to were making sure to avoid interference with the rocket, including its avionics. Another was making sure that the use of LiPo batteries was acceptable by the rocket teams, and making sure to maintain a proper distance from the launch site. For sensor standards, we have a standard from the ASTM which says the accelerometer must be firmly attached to the chassis of the vehicle to maintain accurate acceleration measurement. For wireless transmission regulations and testing standards, the FCC outlines acceptable uses of 5 gigahertz. They say that 5 gigahertz is allowed if operating in a total spectrum of 300 megahertz, and when operating if transmitting power does not exceed 250 milliwatts. Another standard from ASTM E2854 provides criteria for testing to determine if a robot is effective and responsive at certain distances, from which the team will borrow or derive our own testing procedures. For the programming language standard, we will be using Embedded C from Michael Barr's Embedded C coding standard to maintain clarity and organization in this project's code.
In display standards, NTSC format was used for video encoding, and the RCA phono connector was used to route the composite audio-video signal. Here are the electronic communication and control standards, and the connection interface standards. For our project, the sponsor Aerojet Rocketdyne provided us with $500. We used this money on ordering parts, but it was not enough as we had manufacturing costs and additional components to buy. So we spent around $450 out of pocket, bringing the total budget of this project to $956 total.
This project had a number of difficulties and roadblocks that we ran into. We found the first issue to be our budget. We were not given much budget, and the parts shortage made our budget quickly run out, and we had to start spending our own money. Early on in the project, we figured out PCB design to be quite the challenge for us. Our lack of incoming knowledge caused some bad designs to be created that we had to reprint, and when our first designs were being made, the parts shortage made it really challenging to have designs that were able to be purchased. We found that every other couple days, we would make a design, and parts would run out of stock, and we'd have to redesign from the ground up. The capsule and rover, we found working within the tolerance of the rocket quite challenging. We had to do a lot of planning beforehand before we started any cutting for our manufacturing. For the RCS and the Rover, we found the remote control and wireless video transmission systems to be very hard to research and figure out what we needed to do to get them to work. And finally, working with a separate team brings its own issues, and we found the design changes that happened here and there to be roadblocks, but nothing we couldn't handle. Finally, we think we gained a lot of skills. PCB design, metalwork, manufacturing, configuring and debugging embedded systems, parsing documentation, which we found to be the challenge at the end of the semester when we were doing most of our coding, and finally creating technical documentation, which can prepare us for the future. Thank you for listening.